Hello friends, welcome to Kishor Premier Academy, one of the most premier institute for GATE, IES and PSU examinations. In this video, we are going to discuss about the atomic structure. This is the third part of the atomic structure. We have already done two videos on the atomic structure. So this is the third video of the atomic structure. So previously we have seen that this will be the nucleus. This is the nucleus of the atom, and this is proton and this is neutron. Now we can say that these are the different energy levels. This is the energy level 1. So I am writing small n equals to 1. So here it is equals to small n equals to 2. This is equals to small n equals to 3. Here it is small n equals to 4. We have also seen that we have denoted the first energy level using the alphabet K, second one using the alphabet L, third one using the alphabet capital M, and the fourth one is denoted by the capital N. Now these are all the energy levels. So I can say all these are the energy levels of electrons. Now in each energy level we can see there are different subcells. So in the n equals to 1, that means the first energy level there is only one subcell. So here it is only one subcell. So I am writing there it is having only one subcell, that is S. Similarly, in the L energy level we can have only S and P subcell. So I am writing here L will contain two subcell. First one is S, the second one is P. Similarly, the capital M energy level, that is n equals to 3, will contain three subcells Sp and small d. So we can say it will have three subcells. First one is S, second one is P, third one will be D. Similarly, for the capital N energy level, we will have small s, p, d, f subcells. So we can write here the subcell names as small s, p, d, and f. So these are the subcells of different energy levels, and in each subcell we have seen that these are the orbitals. We have already discussed about these orbitals, and in each orbitals there are different energy states, two energy states. So each orbital is containing two energy states. So we can write here that the energy states, which are the energy states? The energy states is this one, and the energy states is this one. So we can see that each orbital is containing two energy states, and each energy state will contain one electron. So each energy state will contain one electron. So these are the things that we have already seen in the previous videos. Now we can say that we can put electron can reside at these energy states. So these are the electrons that can reside at the energy states. Now there can be several electrons inside an atom. So we have to distinguish each and every electrons. That means electrons must be characterized. So we need something that by which we can characterize different electrons. So what are the possible way by which we can distinguish or we can separate each electrons? Generally, the electrons are characterized by four parameters inside the materials. So let us see. The materials. The first one. So we can say right now that the electrons are characterized by four parameters inside the semiconductor, inside the any material, inside any material. Now, what are these four parameters? These four parameters are generally termed as the quantum states of the electron. So we can say that these four parameters are called as the quantum states of the electrons. So these are the quantum states. So these four parameters are called the quantum state. For the case of electron, there are four quantum numbers or quantum states or quantum numbers. So what are the four quantum numbers? Let us see the quantum numbers or states. Generally, for an electron, there are four quantum numbers. So the first quantum number is called the principal quantum number. Generally, it is denoted by small n. The second quantum number is the azimuthal quantum number. So the azimuthal quantum number is denoted by small l. Then comes the magnetic quantum number. The magnetic quantum number is denoted by m suffix l. The last quantum number is the spin quantum number. The spin quantum number is denoted by m suffix s. So these are the four parameters by which we can distinguish each and every electron. That means if we have an electron, then that electron will be denoted or identified by these numbers n, L, Ml, and Ms. Every electron have phone numbers. By these phone numbers, we can identify them. So let us see what is the principal quantum number. So if we go for the principal quantum number, which is denoted by small n, then this principal quantum number is nothing but the orbit number, or we can say the energy level number, or we can say the shell number. We have already seen what is shell number and what is energy level number. So the principal quantum number defines the energy of an electron. The energy of an electron. So we have already seen that every atom, inside an atom there is a nucleus. Inside the nucleus there is neutron and proton, and around the nucleus there are some orbits in which the electrons are rotating. So these are the orbits in which the electrons are rotating around the nucleus. So in this case, you can say that for the first orbit n equals to 1, for the second orbit n equals to 2, for the third orbit n equals to 3. So these are the energy level number, and this energy level number is nothing but the principal quantum number. So two electrons having the same value of n, then we can say that they will have same energy levels. So this was the principal quantum number, which is nothing but the energy level number. So if an electron is residing at this energy level, and if an electron is residing at the second energy level, and if an electron is residing at this third energy level, then for the first energy level we can say the principal quantum number is equals to n equals to 1. For the second electron which is residing in the second energy level, the principal quantum number n will be equals to 2, and for the third one the principal quantum number will be n equals to 3. Hence the principal quantum number is nothing but the energy level number or shell number. Now let us see the azimuthal quantum number. So if we go for the azimuthal quantum number, the azimuthal quantum number is denoted by small l. So the azimuthal quantum number is a quantum number which denotes the subcell number. We know that each and every energy level will contain different subcells. So it is found that the electrons belonging to the cell have different boundary surfaces. So we can say the first point here that electrons belonging to different subcells have different boundary surface plot. That's why the subcells are different. And depending on the nature of the boundary surface plot, we say there are different subcells. Some typical boundary surface plots are like this. If I make a plot, then if I draw it in the 3D diagram, so let us draw it in the 3D diagram. This is the second plot I am drawing, and the third nature of the plot is like that. These are the three axes or coordinates. Now, for the first plot, one type of boundary surface plot that is found inside the atoms of the electrons, it will look like it can have a spherical boundary surface plot. It can also have some dumbbell-like shape, or it can have a double dumbbell-like shape. Double dumbbell-like shape is nothing but this one. This is the double dumbbell-like shape. You can see they're in the different coordinates. So the first plot is nothing but a spherical surface plot. The second one is the single dumbbell plot. Single dumbbell surface plot, and the third one is a double dumbbell surface plot. These are the different types of surface plot that we can find for the electrons that are belonging into different subcells. So which subcells will contain which type of boundary surface plot? Let us see that. So generally, for the S subcell, S subcell contains the spherical boundary surface. Similarly, the P subcell contains the single dumbbell like boundary surface plot, and the D subcell gives the double dumbbell like boundary surface plot, and in the F subcell it is some complicated shape. I am not naming that. It has a complicated surface plot. Which is not needed for the electronic devices, just it is a complicated surface plot. Now Since the boundary surface plot of an electron in the S subshell is spherical, so they will have a different azimuthal quantum numbers. And we know that the azimuthal quantum numbers is denoted by the small l. For S subshell, the L value will be 0. For the P subshell, the L value will be 1. For D subshell, the L value will be 2. And for F subshell, the L value is for 3. So these are the different azimuthal quantum numbers for different subsets S, P, D, F. So we have already seen that if I make a chart like this is the principal quantum number, and here we are saying the subcells. What are the subcells that the energy level contains and the value of A. Now for this case we can say that if n equals to 1, that is for the first energy level, n equals to 1 contains one subcell only, that is S. So the L value will have only 0. Similarly, for the second energy level, we know there are two subcells. So for S, the L value is 0, and for P, the L value is 1. Similarly, if we go for the third energy level, we know there are S, P, D subcells. So for S subcells, we will have L value equals to 0. For P subcells, we will have 1, and for D subshell, we will have 2. So we can see that the value of L is nothing but n minus 1. That means the value of L is ranging from 0 to always n minus 1. So this is the range of azimuthal quantum with the principal quantum number. So from this case we can see that if we have the principal quantum number as n, so this is the principal quantum number qn means quantum number, then the azimuthal quantum number, that is L, will vary from 0 to small n minus 1. This is an important conclusion. Now let us see that what are the magnetic quantum numbers. So for magnetic quantum numbers, let us see what are the magnetic quantum numbers. So the third quantum number is the magnetic quantum numbers. The magnetic quantum numbers is denoted by m suffix. So this is the magnetic quantum number, and the magnetic quantum number, to understand the magnetic quantum number, we have to understand that, let us take, we know that if we take the S subshells, so let us first consider the S subshells. So for the S subshells, we know that it will have the boundary surface plot looking like this. Spherical boundary surface plot. That means if I draw it, it will look like this. This is the boundary surface plot for S subsets. Now, magnetic quantum numbers means how many orientation is possible for the boundary surface plot. So we can say that magnetic quantum number means different orientation possible for the boundary surface plot. This is the meaning of magnetic quantum number. So a spherical boundary surface plot will have only one orientation. That's why the ml value for the S cells is always 0 because it is having only one orientation, and this ml value denotes the number of orbitals. Number of orbitals in subsets. We already know that the S subcell contains only one orbital. That's why the ml value is 0. Originally, it comes from the fact that the orientation of the boundary surface plot, that is the spherical boundary surface plot, having only one type of orientation for S subsets. Similarly, if we go for the P subcell, then P subcell. So in the P subshell, we know that the boundary surface plot is a single dumbbell shaped plot. And the plot looks like this. If I draw the plot, the plot looks like this one. This is a single dumbbell shaped plot. Now this single dumbbell shaped plot can be of different orientation. It can have three types of orientation. So what are the three orientation? So if I draw the axis first, so this is the first type of orientation. Let us draw the axis first. Second type of orientation. And let us consider it as a third type of orientation. Now, single dumbbell shaped plot can also be oriented like this. Single dumbbell shaped plot can also be oriented like this. So we can see there are three types of orientation that is possible for a single dumbbell shaped boundary surface. This type of plot where the dumbbell is directed, if I denote it as the z axis, it has the x axis and it has the y axis for all the cases, then this type of plot is known as the pz orbital. This is py orbital and this is px orbital. So we are having three types of orientation possible for the p subshell. That's why the p subshell will have ml value of three values. So ml will have three values because we have three orientation. So what will be the value of ml? The value of the ml will be 0, plus 1 and minus 1. So these are the possible values of ml for the p subshell. Similarly, for the d subshell, if we look at the d subshell, for d subshell, the orientation or the boundary surface plot looks like double dumbbell plot, and this double dumbbell plot can have five orientation. I'm not drawing here five types of orientations, and these five types of orientations gives us the value of ml as five different values. That's why the ml value, that is the magnetic quantum number value for the d subshell, will be 0, plus 1, minus 1, three values, plus 2, minus 2. So these are the five possible values for the d subshells. Similarly, for the f subshells, we will get the ml value as 7 values. What are the 7 values? Minus 3, minus 2, minus 1, 0, plus 1, plus 2. So these are the possible magnetic quantum numbers, and magnetic quantum number is nothing but the orbital values. So we know that if I make a chart right now, then in the first column I can give the principal quantum number. In the second column I am giving the subcells, name of the subcells. In the third column I am giving the value of L, and in the fourth column I am giving the value of ml. So in this case, if n equals to 1, that is the principal quantum number, let us denote not only L. In the fourth column, let us take the surface nature of the surface plot. Surface plot nature. Next I am taking number of orientation, number of orientation, then I am taking the ml value, then I am taking the orbital number. So these are the columns that I am taking right now. So let us define now that if I take the principal quantum number n as 1, so in that case we know for subcells in the first energy level we'll have one subcell, and the S subcell will have the L value as 0. The surface plot belonging to the S subcell will be the spherical, and this spherical plot will have only one orientation. That's why the ML will have only one value 0, and we know that the number of orientation is nothing but the number of orbitals, and we already know that the S subshells contains only one orbital. That's why the only one orbital. Next, take us the second energy level. For the second energy level, we know there will be S and P both subcells. So the L value, if I write the P in the below of S, so for S subcell, we will get the energy value L value as 0 and the P value as 1, and for here we will get spherical, and here we will get single dumbbell shape. So single dumbbell shape can have three orientation. That's why we will get ML as 0, -1 and +1. That's why we will get 3 orbitals. Similarly, for the S subshells of the second orbit, we'll have like this 0. All these things are similar to the knowledge that we have gained earlier. Now let us take the third one. So in the third one we have got the three subcells. I am denoting like this. Three subcells are there: S, P, and D. So for the S subcells, it will be similar. That is spherical, and the number of orientation will be 1. That's why the ML value will be 0. Then total number of orbits in the S subcell will be 1. Similarly, for the P subshell, the L value is 1, and it will look like the surface plot will look like single dumbbell plot, and the single dumbbell plot will have 3 orientation, and that's why we will get 3 values of ML and +1. Hence, the number of orbitals will be 2. Now comes from the D subshell. So for D subshells, we know the L value, that is the azimuthal quantum number. Azimuthal quantum number is 2, and the azimuthal quantum number comes from the fact that the D subshell will have the surface plot of double dumbbell like shape. Double dumbbell like shape will have 5 different types of orientation. That's why the total number of orbital values inside the d subshells will be 5 and the ml value will be -2, -1, 0, 1 and 2. So these are the different energy levels. I am not going for the n equals to 4. We can also draw that n equals to 4. So from this case we can see that the ml, that is the magnetic quantum number, always has the value from -L to 0 to +L. This will be the range of the magnetic quantum number of the electron inside the atom at any subcells of the energy level. Now let us see what is the spin quantum number. In the spin quantum number case, if we denote the spin quantum number, that is denoted by ms. Spin quantum numbers comes from the fact that the electrons, suppose these are the electrons, and these electrons always rotate about their own axis. They are rotating about the nucleus and also they are rotating around their own axis. So these electrons can rotate in this direction or they can rotate in the clockwise direction also. So if any electrons, suppose take an electron, this is an electron, if this electron is rotating in the, suppose the electron is rotating in the clockwise direction like this, then we will say that this electron will have the spin quantum number as +half. And if there is another electron which is rotating in the anti-clockwise direction like this, then it is said that it will have the ms value of -r. So two possible values of ms is there for the electrons. So by these three numbers we can identify any electrons. That means let us go back to the energy level diagram. So if we go back to the energy level diagram that we have seen in the first case, so this is the energy level diagram. So here, suppose if we want to denote the electron here, and suppose we have an electron here, then for this electron the four quantum numbers will be, if I write, the first one will be n, second one is l, third one is ml, and the fourth one is ms. So for n means the energy level number, that is 3. And the L means the energy, L means the subcell number, and here it is the subcell in the D, so L will be 2, and the ml value will range from minus, ml will have the value ranging from -2, -1, 0, 1, +2. And ms, either ms can have plus half or minus half. Similarly, these electrons can have quantum numbers like n equals to 3 and L value will be 0. Similarly, we'll have the ml value, we'll have the mf. So in this way, we can identify the different electrons inside the atoms. And last of all, do not forget to subscribe and like our channel to get more videos like this. Thank you.